All right, in the previous class, we have seen that pumping a solid state laser by a diode laser is much more advantageous compared to pumping it with a flash lamp. Let me once again very briefly explain to you as to why so. You see, the usually rod-shaped host material usually resembles a very small pencil in shape. So this is our cylindrical laser rod, and the diode laser, this is a very qualitative representation, provides a directed beam of light which can be very well guided into the host. This is the diode laser output. Diode laser is just another name of semiconductor laser. It can be very well guided into the laser rod. And therefore, the pump photons provided by this diode laser would have very good spatial matching with the light emitting atoms which are embedded into the host. So, very good spatial overlap of the light and the absorbing atoms. But that is not all. The wavelength of the dye laser is chosen to approach as closely as possible the pump wavelength. That is, this is the ground level, this is the pump level, this is the upper laser level, this is the lower laser level. So we pump first the molecule, this diode laser will pump the atoms from the ground state to the pump level. Suppose the pump wavelength is lambda p. So the wavelength of the diode laser must be as close as lambda p. And the absorption has a width. And so this is the absorption feature. This is the absorption, and this is frequency, absorption as a function of frequency. And this is wavelength lambda p, the line center of absorption, which is lambda p. The wavelength of the diode laser and its emission width, wavelength of the diode laser lambda will be very close to lambda p, and the emission weight and the absorption weight would nearly match. So therefore, almost all the photons which are contained in the diode laser beam will be absorbed by these absorbing atoms. So not only there is a good spatial overlap, but there is an excellent spectral overlap as well. Spectral overlap as well. So it will be very efficient utilization of the pump photons. Now, in contrast, let us consider the case of pumping by a flashlight. So now you do not have the diode laser, you have flash lamp. So let us assume it is a tubular flash lamp. Now, flash lamp, unlike the dart laser, would emit light that will travel all around. So you can very well appreciate that coupling of these photons into this host medium will be very poor, and you may have to take some special measure to direct as much photons as possible into this. So there will be poor spatial overlap. And that is not all. Because it is a conventional source of light, so its emission will be very wide. And in comparison against it, you consider the absorption feature of these absorbing atoms. So only a small fraction of photons of this flash lamp, which lies within this frequency domain of the absorption, will only be absorbed by these atoms. Majority of the photons which lie outside this absorption domain of these atoms will just escape unabsorbed. Therefore, you can appreciate the fact that when a solid-state laser is pumped by a flash lamp, the pumping will be much less efficient. Utilization of photon will be much less efficient as compared to the case of pumping it with a dart laser. Therefore, you can very well appreciate that the pumping geometry employed in the operation of a lamp pump solid-state laser differs considerably from that for a dart pump system, because you will have to ensure that you are able to direct all these escaping photon back into the host. So then, let us turn our attention to now pumping a solid-state laser with flash lamp. This is the active medium, that is the host into which the atoms, light-emitting atoms, are embedded. So this is the medium which has to be pumped by the photons emitted by this flash lamp. The lamps used for pumping Nd-Yag laser, so we are considering the case of neodymium-Yag laser. Neodymium-Yag. So neodymium is the light-emitting atoms, Yag is the host crystal into which neodymium is embedded. Usually tubular and in shape, and runs along the entire length of the active medium, to increase the efficiency of pumping. Placing this assembly, that is the flash lamp and the laser rod, inside a cylindrical housing, inner side of which is reflective coated, of course enhances the pumping efficiency that we have seen even before in one of the earlier classes. And normally the reflector actually has an elliptic cross section. So this is the top view of the experimental system, and this is the end view. And the jacket that is, you see, around this laser rod is basically the tube through which the coolant fluid flows to remove the heat that is dissipated into the laser rod. So normally the reflector has an elliptical cross section, as you can see from here, from this end view. And the lamp and the rods, this is the rod, this is the rod, and this is the lamp. This is the lamp, this is the rod, this is end view, are placed along the two foci of this ellipse. This is one focus, this is one focus. The lamp and the rod are placed along the two foci of this ellipse. This allows a majority of the light emitted by the lamp, rather escaping light, which doesn't travel towards the rod, emitted by the lamp to be directed by the reflector of the rod, to be directed by the reflector of the rod. You see, the light which suppose travels in this direction, because this is a focus, these two are two foci of this ellipse, so this will be directed. The light which are emitted in any other direction will be directed towards the, so this will increase the efficacy of pumping. Majority of the escaping light can be redirected onto the rod, and it will help in the pumping efficiency, that is, increase the population inversion. The usage of two flash lamps to increase the coupling of the pump photons into the active medium is also not uncommon. So what is done here? This is reflector is fabricated by fusing two cylindrical enclosures into one, each with an elliptical cross section. Both have elliptical cross section, as you can see, and they are fused into one. And the two ellipses are so joined as to have a common focus. This is the common focus, along which the rod is placed. So this is the rod which is placed along the common focus of these two ellipses. The two lamps, these are the two lamps, are now placed on the two remaining focus of these two ellipses. So then you can appreciate the fact that this arrangement will readily offer an energy loading that is twice as large as that which is possible with a single lamp. If you have used two lamps, so you will two lamps to produce twice as much light as can be produced by a single lamp, and therefore this arrangement will ensure that the energy loading, pump energy loading, is double as compared to the case of one flash lamp. So here again, the light which will escape in other direction would be again directed onto the rod. This will increase the efficiency of pumping. However, there are a number of issues that is inevitable in the operation of the solid state laser when it is pumped with a flash lamp. So let us just see what. You say a substantial fraction of the pump energy, you already know, absorbed by the rod will be realized as heat in its interior following the process of lasing. So why actually, why it happens? You know that, suppose these are our energy level diagram. So this is the pump wavelength, lambda p, and the lasing occurs between these two levels. The wavelength of lasing is lambda L. Therefore, you see, to get a single photon, one photon of wavelength lambda L, what is the photon's energy? Photon's energy would be simply hc by lambda L. you will have to expend a pump energy which will be hc by lambda p. As lambda p is less than lambda L, therefore hc by lambda p, that is the energy that is required to be pumped for the generation of a single photon. So this much, this is the energy difference. So hc by lambda p, that is the pump energy, is more than the energy of the photon that is created. So then this much energy, hc by lambda p minus hc by lambda L, remains into the system, stays back into the system. And you can actually, in this case, lambda p for Nd-Yag laser, the pump wavelength is around 800 nanometer. And the lasing wavelength is 1064 nanometer. So if you can plug in these values, that is the Planck constant, velocity of light, and lambda p and lambda L, you can find out that appreciable energy actually stays back into the system, and which this substantial fraction of the pump energy then is eventually absorbed by the rod, which will be realized as heat in its interior following the process of lasing. Now this waste heat that host eventually conducts away, because host, we know that it has excellent thermal conductivity. So it rapidly conducts away this heat onto its surface. And this is removed by flowing a coolant fluid over it. As you can see, this is the jacket around the laser rod, and coolant flows through it and remove this heat which is conducted away onto the surface. As in case of gas laser, here too the hot fluid discards the waste heat in a heat exchanger. Helical flash lamp, where the rod lies along the center of the helix, which, as you know, powered the very first laser, have not gained much popularity due to the hindrances of the positioning of the mechanism for flowing coolant over the hot surface of the rod. See, this is your rod, and if you use a spring-shaped, that is helical flash lamp, and then place the rod, this is the rod, laser rod, at the center of the helix, then it will be difficult to place the jacket around this rod because of the presence of this spring-shaped flash lamp. And that is why this has not gained much popularity. And the solid-state lasers usually is pumped by a tubular shaped flash lamp. And of course, there can be number of flash lamps if you want to improve the efficiency of pumping. And as I showed, in this case, 2 flash lamps are used, and you can actually use multiple flash lamps to enhance the efficiency of pumping. Now, unoptimized cooling of the laser rod lifts its center hotter than the surface, because the more heat would be generated at the center, which will result in the occurrence of a refractive index gradient, because this is the cross-sectional view of the rod. Center is hotter and the periphery is cooler. So there will be a temperature gradient. This will be hotter, center will be hotter, and the periphery will be cooler. So refractive index depends on temperature. That means there will be a refractive index gradient as well across the diameter. So this will thus give rise to a thermal lensing effect. This will now behave like a lens. Thermal lensing effect, which will degrade the spatial quality of the laser beam. So this is called thermal lensing effect. However, there would also be mechanical stress that would be developed because of this effect. You see, this is your laser rod cross-sectional view. The center will be hotter and the edges will be cooler. So center will be expanded more, the central region of the rod, and this will be expanded less, the edge, because its temperature is less. So that will develop a mechanical stress, due to which may lead to even cracking of the laser rod because of uneven expansion across its diameter. So these are the issues. Now, against this background, let us now turn our attention to pumping a solid-state laser with the help of a dart. You see, the lamp pump solid-state laser quite expectedly suffer from poor electro-optic efficiency because the pump photons are not very effectively utilized here. Lot of pump photon just be lost to escape absorption. And the electro-optic efficiency normally lies between 0.5 to 1%, very low efficiency. This wasteful expenditure of energy becomes even more significant for a high-power lamp pump solid-state laser. If you increase the power of the flash lamp, then you will waste more energy. So, if you have to generate high power from the solid-state laser, then the energy that you waste is also more. In contrast, when this laser is pumped by the monochromatic and directional emission of the diode laser, it operates with a greatly improved electro-optic efficiency, which can be as high as 10 to 20%. Compare, say, 0.05% percentage of operating efficiency of a lamp pump laser with say 10% operating efficiency of a dart pump laser. There is a factor of 0.5 to 10. There is a factor of 20, which is a very big number. It is no wonder that with the advent of efficient dart lasers, the usage of once popular lamp pumping is on the wane. It is not very popular anymore. Only when dart laser did not exist, it had its use. And in particular, in the operation of high power solid-state laser, even though for low power solid-state laser, the lamp pumping is still in use, but no more so for operating high power solid-state lasers because then you waste much more energy while operating the laser. And in contrast to lamp pumping, the directional emission of a diode laser has also made end pumping of a solid laser feasible. As you know, a solid-state laser can never be pumped by a flash lamp because it emits light all around it. So, no way you can direct this light through one end of this laser rod. However, side pumping is inevitable in the operation of lasers with higher power, even when it is pumped by a diode laser. We will just come to it in a while. So let us now see the experimental arrangement for pumping a laser rod with diode laser. This is the scheme very schematically and qualitatively shown here. The pumping of a laser rod by a single dart laser through one of its ends, which is also called longitudinal pump. As you can see here, the pump beam, this is the dart laser, this is the pump beam, is coupled to the laser rod, this is the laser rod, through one of its ends. We are coupling it through this end of the rod. This is used widely for low power laser. We will come to that. Why? So the emission of the dart laser is optically coupled with this lens. It appropriately focuses it, and it is coupled into the laser rod through a dichroic mirror. Through a dichroic mirror. You see, the dichroic mirror essentially, now we are again considering Nd-Yag laser. Nd-Yag laser, which is pumped at around 800 nanometer, and the lasing occurs at 1064 nanometer. So now the dart laser operates at around 800 nanometer. Actually, 808 nanometer is the diode which is available closest to this pump wavelength. So 808 nanometer is the wavelength of the diode. So this dichroic mirror would transmit 808 nanometer, 808 nanometer. This is 808 nanometer. This mirror will transmit this. So it will be very well coupled, as we have said, that so atoms will be excited and population inversion will be created, and then that will be the beginning of lasing at 1064 nanometer. As the population inversion occurs between these two levels, spontaneous emission will begin, and that will seed the stimulated emission. You now know this very well. So these photons at 1064 nanometer, as they shine on this mirror, the mirror should offer very high reflectivity to this. Only then oscillation of light back and forth would be possible. This is the output mirror, which has appropriate reflectivity and some transmission loss to couple out the laser beam. So then this special dichroic mirror transmits 808 nanometer but reflects almost 100% 106 nanometer. This is a special mirror. So this mirror offers high transmission at the pump wavelength and high reflection at the lasing wavelength. The pumping geometry intrinsically offers here a good spatial overlap between the pump photons and the light emitting atoms dispersed uniformly within the host. This in turn yields a high gain, making this scheme attractive for use as an optical amplifier as well. See, when you have placed this gain medium inside a cavity, in this case the cavity comprises of this dichroic mirror and this partially transparent. So there will be oscillation and you will generate an output. But because this has a very high gain, because the pumping is very efficient, you can build up very high gain at 1064 nanometer wavelength between these two. So it can be used also as an amplifier. I just very quickly tell you this. How do you use it? So this is your laser rod, and this is the diode laser, and this is the coupling mirror. So 808 nanometer 808 nanometer is coupled into it, and you create gain. That means you have created population inversion between the upper laser level and the lower laser. You have transferred, so created population inversion between these two levels, and this occurs at a wavelength of 10. The spacing between this is 1064 nanometer in wavelength. So you have created gain here. You have created gain. Now, if you can shine this medium by a beam of light with photons that has a wavelength 1064 nanometer, then if you can pass those photons through this, they will be amplified. If this photons travels through this medium, 1064 nanometer photon, they will stimulate this and force them to come down, and by virtue of stimulated emission, their number will increase. You know how an amplifier works. So how do you couple it into it? So you use once again a special dichroic mirror. So you have your 1064 nanometer. nanometer input. This reflects 1064 nanometer and transmits 808 nanometer. That needs to be transmitted because we will have to create gain in this. Now 1064 nanometer is reflected by this, and this also transmits 104 nanometer. 104 nanometer will travel through it, and as it passes through it, it will be amplified. This number of photons will keep on increasing as a result of stimulated emission. And there will be much less absorption because the lower laser level is not populated. So this beam will be amplified. You will have an amplified beam at 1064 nanometer. So that is how you can even use this as an amplifier. Come back to the operation of this as a laser. The laser rod is usually enclosed between the dichroic mirror and an air window. This is an air window which allows 1064 to pass through it. In case of a compact and small laser system with modest power, the output mirror can be directly mounted on the rod in place of an air window. So you can actually mount the output mirror directly here for a small and compact laser system. And then there won't be any need of any air window. This is directly mounted here. But not for a very compact laser, probably this would be a better option. So this is how you can make a end pump and a solid state laser that is end pump by a single dart. I think I should end here today, and the next class we will begin right from here. That is solid state laser, which is end pump by a single dart.